else?
Interview? Are we gonna go over the turnover phrase? What the turnover is?
Yeah.
Yeah, we're gonna go
Today,
over that.
yeah,
Okay.
we'll go over that. Anything else? All right, well, then we can begin. I was saying that I tried to change the font back. I'm not sure why it keeps coming out as an alien. But it's supposed to be capital. So that's the real constant. It's supposed to be a rate constant. So whenever you see it, that's where it is. I'm not sure why it keeps popping out. And if Arial cannot be recognized, then why else can be recognized? That's like a font that they need to recognize. I'm not sure what's going on. Maybe it's just a symbol. Anyway, so today we're going to talk about enzyme kinetics. And most likely, we'll be able to talk about enzyme inhibition as well. That's going to be towards the end. Based on how much time we spend during the class, we'll see how much we're going to cover of inhibition. But the goal is to cover it. For us to talk over, to talk about it and discuss it. And so we'll deal with a lot of graphs today. It would really require for you to, when you go home, to really go over this again, slowly, don't rush it, and make sure that you understand the details so that it would make sense. Otherwise, you'll just have to memorize it and it wouldn't mean anything to you. And when you have to explain things, you wouldn't know what to say. So just take it slow. All right, so we've talked about last time that, well, basically, rate means speed. And so, enzyme kinetics deals with rates, or with speeds of reactions, and how that rate or speed changes over time. In other words, whenever we have a speed, that's a change over time. Whatever that change may be, it can be distance, it can be concentration, over time. That's a rate. And so from this equation, you can see that the rate of a reaction is proportionate to the rate constant and the concentration of the substrate. Well, obvious question would be, how do they relate? Proportionally or counterproportionally? Well, it's obvious from the equation that it's proportionate relationship. So every time when you look at an equation, it would be nice if you make that conclusion. How do those two relate? Proportionately, counterproportionately, or directly or inversely proportional. In this case, the increase of substrate will lead to an increased rate. And we know that that's only at a certain point. Right? Okay, so in our particular example today, you've actually done this kind of curve. Do you remember where you've done this curve? In Chem 106 lab, when you had to do catalysis. Right? Remember you were making, well, I'm not sure how the labs are now, I think hydrogen peroxide. So you were retaining, well, you were right, you were using different metals, and you were actually using an enzyme pyrrolate, I believe it was called. And so you were trying to generate a product, and you were detecting gas pressure. Right. And you look these graphs. Okay, so what do those graphs mean at your pressure? So each one of these graphs, each one, is a separate setup where we have the same amount of enzyme, okay, but different amount of substrate at the beginning of the reaction. And then the reaction starts, and we detect the concentration of product over time. That's a rate, right? At this starting concentration of substrate, at this starting concentration of substrate, and at this starting concentration of substrate. Okay, so what do you need? What do you see? That the rate of production or the concentration of product increases over time with the increase of substrate, which conforms to this equation. But there is something else very interesting in this graph. What part of the graph did you guys use in your Chem 106 lab? I don't expect you to remember, but there is a portion of that graph where the enzyme works at an optimal rate, where over time the concentration of product or the rate of production of product is the same. Where is that portion?
Tangent.
See it again?
Tangent line.
That's right, it's a tangent, but there is that relationship between the concentration of product and time that is being retained over a certain period of time. In other words, the rate of production of product is the same over time. But that is right here at the very beginning, where we have a linear portion in the graph. And that portion over time we have the same rate of production of increase of product. So that rate of optimal production is called a steady state. In other words, the rate doesn't change for a certain period of time. At the steady rate, steady state kinetics. Okay, then if we take that rate, and that's what you did as well, you cut everything off, you just looked at the slopes of the linear portions, which was the rate. You took that number, or you can take that number, and we plot it against the initial concentration of the substrates, we get this relationship that describes the initial velocity, which is this, of the reaction, initial time, at the given substrates the reaction has been performed. And we see this. What can you tell me about, when you see a graph like that, what kind of thoughts go through your mind in terms of the relationship between velocity, initial velocity, and concentration of substrate? Just think about it. We'll go over it later. Okay. Yeah, okay.
I got a question on this one.
Sure.
Because wanted to try it, and it's worked once, and one time it didn't. Because it's really hard to actually find the initial velocity at the beginning of your graph, because it seems like just by looking at the beginning, where you're trying to see the linear relationship, if you're even off by 1 point on the plot, that's going to have a great variation on your Km or after Vmax. Is it possible if you took your first 3 points of whatever graph you obtained and deliberately almost force a linear line by plotting in the rest of the results, could you use that as your initial velocity to plot against your substrate concentration to get a better result? Or is that kind of skewed a little bit?
Well, experiment by experiment will vary greatly.
Yeah.
I mean, even here you can see, I mean, you can almost say that any portion of this graph can give you a linear relationship.
Mm-hmm.
You know,
Yeah.
I mean, it's very, the linear portion is very small compared to this one or this one.
Yeah.
Now we're talking about initial velocity. So yes, in a way, for some graphs, you could take the first few points. You know, if it's hard for you to really determine a linear portion of more points than 3, 4, 4, something like that. Because this one might have a lot more, this portion of it. But
Yeah.
this one is very small. So it's going to be hard. But again, you know, since we're talking about initial velocity, where we can make the assumption that we have unlimited amount of substrate, since we just barely started the reaction, you can make that assumption, that the first few points are actually the linear ones. Good question. These are very practical questions, and sometimes theory and practice are hard to match. This is ideal, almost. All right. So, okay, remember that, you know, it's all these are all rates, you know, all rates. So again, Michaelis-Menten, well, the The steady state kinetics was first described and proposed by Cornelis and Mendel, where they generated a graph that looks like that. In other words, a relationship between the initial velocity and the substrate concentration. Now, for a given reaction, simple enzymatic reaction, we have an enzyme, we have a substrate, and thus enzyme and substrate form an enzyme-substrate complex described by a rate constant kappa 1. The enzyme-substrate complex can either break down back to its members, or substrate and enzyme, with a rate constant of kappa -1, or it can become enzyme and a product with a rate constant of kappa 2. Now this is kappa -2. That's the constant describing the reverse reaction, or the enzyme product forming an enzyme-substrate complex. This reaction is possible. However, we make the assumption that at the very beginning of the reaction, the concentration of product is so small that in essence there is no reverse reaction at the very beginning. You have large quantities of substrate with very small amount of product. This will change over time, but at the very beginning we can make that assumption and we can disregard kappa -2, which will simplify some of the following conclusions.
So then, well, I mean, maybe this is a given because it's something that there's always going to be driven towards the different product.
We'll make that assumption that at the initial stages, but obviously at any given point in time, the reverse reaction goes as well. So at the very beginning, we could say that E plus S will go forward to ES, which will break down or move forward to ADP. But we'll disregard that at the beginning. But later on, that will be definitely a factor. And there will be an equilibrium unless we change something in the reaction and it's driven towards one or the other. Okay. All right. Yeah. Dave.
On the ES max, does that mean that all
Well,
of the enzyme is down?
Right. That's the maximum possible complex. In other words, the maximum velocity will be dependent on the rate of disappearance of that complex at a maximum, when it's at its maximum. That's what basically describes the maximum, the Vmax. But now the Vmax, though, has a much better representation or explanation. This is just a formula that describes Vmax. But Vmax is what? The rate, or the maximum rate at which an enzyme can perform. In other words, all available spots are already occupied with a substrate and it's working at its maximum speed. There's nothing else you can do. Now notice another thing, that this graph never reaches or touches Vmax. Why do you think that is? It actually, we're never going to see it, but it is possible, but only after calculating. This, if you extrapolate this graph far left, I mean right, it will eventually reach it. But you have to have a very long graph. But eventually you will reach it. However, on graphs like these, you will never see it cross. Now, if you do experiments, you might see it cross. But you shouldn't. That's just experimental error. Just like what Ben described, right? That's like reality in theory. Theory, you should reach it, but after a very long time, at very, very high concentration of substrate. That's when you